I recently dug out this monstrosity of a power bank, and I thought, since I'm taking a short break from working on the Z80 project, because routing a fully buffered processor card on a single layer is very hard and also somewhat annoying. But what is this? This is, well, a very crudely made power bank I did a couple years ago. And what it basically has is, I'll open the lid here. It has 2 boost converters, and it has a comparator chip down here, and a 7-segment display up here. And the 7-segment display is, I think, diode steered. It's going apart. And basically, the comparator just checks the voltage on these batteries. A little LED on it, and it puts out an H for high if it's well charged, and an L if it's not charged. And then it also has a relay glued in here as a basic cutoff. And yeah, then it has a something output with this boost converter module here. Lighting isn't too great. Let's get some more light here. Yeah, that's a bit better. It's not even connected to the port anymore. This is abandoned this project a while ago, but I thought, while I'm at it, I could make this a little nicer and add some bells and whistles and add some proper circuitry. This is very crude, and there's a, I don't know if you can see it on camera, but there's a MOSFET glued in there, which is, I suppose it's switching the relay. Yeah, this I made more than 10 years ago, I think. It's very old, but my skills have improved, and so also, worst thing about this is it has no internal charging whatsoever. You have to come in with a charger and charge it up. So I basically want something that has, well, let's just write it down first. Charging, circuitry, 5 volt and 12 volt output. It's always nice to have 5 and 12 volt. 5 volt, I want to have at 2 amps, and 12 volts, yeah, maybe what, 100, 200 milliamps, just to I don't know, light up a LED module or something. Whenever you need 12 volts to do something, maybe for high voltage programming or something. Yeah. Also, would be nice to put an audio amplifier in there. So that you can actually, if you're taking this out as a power bank, you can actually listen to some music with it. And we want this to have some sort of Bluetoothy input. I want a display of some sort that is a little better than having an 8 on here that just lights up when it's fully charged. And what I thought I'd do is I basically recycle the idea of the flashlight I built a while ago, which is this thing here. It's currently plugged into its charger. That basically shows you the charging state. This is almost full now with these IV25 vacuum fluorescent displays. Sort of Russian display modules that are very cheap and look very good. I like them. So yeah, some sort of nice display, and then we'll see what we'll also add. But these are the sort of the basic specs for this. So let's go into lithium-ion charging, and we'll do this, I think, somewhat crude, but not all that crude. And the idea with lithium-ion charging is you need a constant voltage to charge it. Each cell can't go over 4.2 volts, and you also need to have it current limited to about, in case of, well, these cells, about an amp or two per cell would be good. So if this is 4, 8, 12, 14 amps, because those are all in parallel, which is also not that great. Since these displays over here, they require high-ish voltage to light up, so 15, 16 volts would be perfect. I think you're supposed to run them at something like 30, but they are fairly bright at 15 volts. I tried this for the flashlight project. So I think what I will do, since the audio amplifier that we're going to stick in there is also going to need something more than 12 volts. I'm not sure about what amplifier I want to have in there. Maybe even Class D, maybe something else. But it's definitely going to need a higher voltage. And since I really don't want to put one of those boost converter modules in there, I think what I want to do is have series pairs, and then just cut out this battery and have 3 in series, 2 in parallel, which is a pretty hefty power bank that could supply anything for a long time. Well, almost anything. You can probably charge your phone up from this a lot if you really wanted to. So we need a constant voltage, and we also need that current limited. So for low-ish charging currents, I think we could actually get away with just using an LM317, which looks like this. You've all seen it before. And this will actually hold a constant voltage, but also current limit at exactly 1.5 amps. Now, this would be pretty good. It will take 2 hours to charge up that battery, roughly. So this would work out just about fine. So let's just sketch that down here. We'll have our input like this, and it goes to our LM317. With its voltage divider. Sometimes I feel like this is the power supply design channel, but, well, the crude power supply design channel. Anyway, let's build another power supply. And we'll have an output capacitor here. And this will just then just go to our battery. But the other problem that you have with pairs of batteries, if you want to charge them, is you can't make sure that they all drain equally. You know, what I did here is a mistake. You can't make sure that if you have a couple of these batteries in series, and other people have explained that better than I do, but if you have this in series and this battery has a capacitance of 750 milliamps and this of 1600 milliamps, then this will drain much faster than this. And if you charge it up and discharge it, you'll actually overvolt this battery long before this one is charged. so this is no good. You need to have something that's called balanced charging. If you don't know what that is, go look it up. Other people have explained this better than I do. So what we basically need is a large 1.5 amp Zener diode over here that 4.2 that basically once this cell here hits 4.2 volts, everything over 4.2 volts will just go straight through here into the next battery, which is also connected to this. So the batteries are in between here. And then you'd have your next battery here. And you'd have your next huge Zener diode here. And so on till you actually get down to ground level here with your last battery. But the thing with having Zener diodes that can pass an amp is not going to happen. Either very expensive and all sorts of problems. You don't want to do that. Commercially, this is actually done with just having a little control chip and then having a FET that bypasses it once it reaches 4.2 volts, which is not too bad of an idea. Could do that, but since I don't have any control chips, I will probably use something else. It's a little bit simpler to implement. And what I think I'd use is this little, it's actually an integrated circuit that comes in a TO92 transistor casing, and this is a TL431, very, very old, very, very popular little chip. And the schematic for this, well, the circuit symbol for this looks like this. It's basically like a Zener diode. It has an additional lead that you can connect a resistor divider to, like this. And then you have your series path resistor here. And then you put this here. And then you can get your regulated voltage from here. This is basically a shunt regulator. And this is exactly what we need here. Instead of this Zener diode, we need a sort of unadjustable shunt regulator. But the problem with this chip is it can pass 100 milliamps maximum. So what we'd have to do is we have to add a transistor, and I'll draw this out in a more orderly manner in a minute. So we basically have a transistor here, PNP transistor, that passes all this excess current for us. And then we'll have a largish resistor here, 330 ohms, that limits the current here, and then this will drive this, and everything will be bypassed nicely, which is just the thing we want, actually. We want this connected to here. So, if you actually draw this up, it would look like this. And you have your transistor here, and basically a voltage divider, and your current current regulator resistor here, and a transistor that basically bypasses the batteries. The batteries are in between here, 1, 2, 3, and you can have many pairs. You just have to rate this transistor for the charging current you're passing through, because this will pass almost all the current once this hits the desired voltage. So if you're charging this at 2 amps, you'd have to rate this transistor to dissipate 1.2, about 2-3 watts, something like that. And that's basically how we're going to do the charging circuit. And I actually breadboarded this up on my little breadboard over here. It's just barely in shot. I have to disconnect the power leads before I can bring it in. I actually only did that for two cells in series, and I had the 2 cells you saw earlier. I had those connected in here, and also this is where I just pulled this chip from. This is connected in here, like something like that. Doesn't matter. Yeah, and these get somewhat hot on this heatsink. These are BD137 PNP transistors. I might, for the final version, choose a little bit beefier ones. But these do fine. I think they're rated up to 2 amps, so that should be plenty enough. But we'll definitely in our final configuration, we definitely have to have this heatsinked, because else we'll burn out the transistors very fast, because they do get somewhat hot. So with the charging and the balancing circuit out of the way, the next thing that I'd like to tackle is the actual power supply. And we can definitely run our... Will you focus? We can definitely run our 12 volt amplifier and a 12 volt power supply directly off of the batteries. We just have to remember to put a fuse in there in case someone shorts it out, so they don't burn down everything. The only thing we really need to take care of is having a 5 volt supply for all the logic and the phone charging and all that sort of stuff. And what I want to use for this is this chip, which is the MC34063A. I've got a ton of them here, and I've used them before. This is one of the few switch mode chips that are fairly well design friendly. You can't do much wrong in your layout to make this not work. This is fairly robust, and there's a ton of applications. This can do step up, it can do step down, up to 1.5 amps peak current if you don't add any sort of external pass transistor, much more if you do. And for the 5 volt step down supply, we're stepping down from about 12.6, and we want 2 amps out. We definitely need peak currents higher than 1.5 amps. So the topology, this is directly from the data sheet, that we want to use is this, where we just have our battery's voltage coming in, current limiting resistor here. I'll just bridge that. I'll probably bridge that. Although I might even put a small resistor in, so this limits to 2 amps. And then, in case something goes wrong with the phone charging port or somebody shorts it out, you don't burn out this chip. And it just loops around, goes to an external transistor. I think I'll use a BD437 here, sort of my favorite medium power transistor. And there's a little resistor here. You need a fast switching diode here. I think I'll use the BA159, which is a little bit overkill for this, but it will work. I mean, in terms of voltage, this goes up to 1000 volts, but it will work. And for this inductor, I'll just use a 3 amp 100 microhenry inductor and a 1000 microfarad cap or something at the output. And this is just a very simple 5-volt power supply. I said I don't think I want to use an LDO or something for the 12-volt power supply, because, well, we don't really need it. The amplifier, no matter what I actually choose later, although it's probably going to be Class D, won't care all that much about the voltage dropping about a volt or so during its operation. Well, if we put a 12-volt LDO in, we burn away some power at first, and then it will do all sorts of nasty things once we get below 12 volts, while the actual Class D amplifier might be rated down to 10 volts. It might be running fine for another half hour. So I think I'll just run this directly off the battery with a fuse. And yeah, I'll put this in for the 5-volt supply. Let's look at the next thing we've got to think about, which is the display tube here, which I want to use to display the left charge, and also maybe some, I don't know, error messages or something. And what this VFD tube looks inside is basically a tube like this, and it has a filament in here, goes across like this, and then it has these contacts, 7 of them, and you can actually see that each of them is connected to a wire that just runs out the back, and it's connected to the front here, and this is coated in a phosphor which lights up when being struck by electrons. And so you actually connect this up to a power source of a couple of volts to make this glow. In this case it's, I think, 1.5 volts, something like that. And what you then do is connect these anodes here to light them up. As you connect them, preferably via a resistor, up to your voltage. And what we could do is just basically put a transistor in here to control this, but a much nicer way is to use something like the ULN 203, which is, I think this was originally meant as a hammer driver for matrix printers, but it's so ubiquitous. It's in everything. It's really, really nice because it's just a Darlington transistor array. Just has a couple of Darlington transistors in there, and all the emitters are common. So you put your resistor here and your power here, and then you just connect those, and these are connected to their own resistor as well, but I won't draw that. So you just come in here, and this is connected to ground, and then you have your input lines that go out to your controller. And this works very well. What you have to think about is that you actually forgot that this is connected to ground, so that you get your electrons basically coming in here, raining down here, and then lighting this up. But what you have to think about that this is, it will invert everything. If this is off, if this is low, this will actually be on because the current is flowing basically this direction. With vacuum tubes, it's easier to think in the actual direction of the electron flow. With everything else, you usually think in terms of current flowing in this direction, but with vacuum tubes, it's easier that way. So, next thing with this is we have 1, 2, 3, 4, 5, 6. This ULN 2003 has only 6 transistors inside, but this actually has 7 segments. So I'm going to do the same thing that I also did on on this project, where these are actually paired up. So you lose 1 digit, but at least they still light up, and it simplifies your control a little. So these are actually connected. And yeah, that's basically that for driving the display. Got our 6 lines here. 1, 2, 3, 4, 5, 6. Yeah. And we could basically just use something like an ATmega 8 or 16 or 32.8 or whatever on Arduino. But this is such a simple job. It actually doesn't justify the expense of a big heavy microcontroller. And also, you should always keep in mind that a microcontroller like this is going to draw a lot more current. So what I think I want to do is use a CMOS shift register like 74HC595 and have these connected to there, and then have the control lines, which is latch, serial clock, and data. Have that going out to a microcontroller. So we save us 3 pins on this microcontroller. Even more if we actually put latch and serial clock on the same pin. So everything that you pump in always instantly latches, and you can actually get away with 2 lines. And then we'll use either an ATtiny 16A, if I can make the software fit, or an ATtiny, one of the bigger ones, I think 45, which is what powers this flashlight. But in retrospect, I definitely could have done it in an ATtiny 16A. I just didn't have any of those at the time. What we also need to do is when the battery voltage needs to come in here and needs to be resistor divided down like this, so that when the battery is all full, we get like 4.5 volts here, so we don't blow up our microcontroller. And this will go straight into the ADC, and then the ADC will basically decide what needs to light up here and send this to the shift register, and there we go. Yeah, that is basically that. So how would you actually drive the 74HC595? Well, I've got a timing diagram here. And this is the serial clock that I just mentioned. This is basically the data in. It's just named serial here. And this is the latch clock. This is less important. This basically, if you want to shift data in, and then you want to decide on the exact time when it's shifted out, so you actually can shift in a set of data and then shift it out all at the same time. For us, that doesn't matter much because you just do this fast enough so you can't see it on this display. If we drive this at 100, 200, 500 hertz, you will never notice that there is actually a dot scrolling across. So can actually ignore this and save us a pin by just tying those two together. So what we need to do is, you can actually see on the timing diagram here, this clock is just running all the time, and if this is high, the serial is high, and this is the master reset. This master reset is also high. We'll just tie this high always. And the clock goes high here. You'll actually get data shifted into the first sort of output register, output latch thing. Then on the here, once this clock is down again, you'll actually get it shifted to the next one. So let me just see here. Yeah, I think this is triggered on the falling edge, although I'm not sure. What I can see from this is what we need to do to actually display numbers from 1 to 7 on this is we've got our serial clock here. Our serial data here. You actually have this high for, I'm just going to assume that it's on the falling edge, for 3 cycles like this, and then switch it off. And we need to make sure that this pulses 8 times, because this is an 8-bit register, and if you don't pulse it 8 times, will actually next time you pulse it, you'll have one bit left here. So if you go back to this, if you pulsed it only 7 times and you started feeding in new data, you'd have this artifact here. Then you'd, with the next clock cycle, shift here, and then it's not good. So we need to basically write this little program that creates 8 of those on one pin, so 8 of those, and then creates an arbitrary number. Now, basically keeps this on for a number of those. So for, this would actually be like 1, 2, 3, like this. And then if you want more, you'll actually just have it longer. And we'll go over the code, how I'm going to solve this. It's probably not going to be the most elegant way, but it works. Let's just go over the code here real quick and start right where it gets interesting, at the beginning of the while loop. I'm just basically copying the zegin is basically the input to this thing. I'm just copying it to another variable so I can decrement that later on without actually affecting the value, without losing the value that I want to display. And then I pull the serial data pin high and enter into a for loop, which is going to run a couple of times. And at the beginning of the for loop, I just decrement the segment, the serial counter, basically. This is just a number, how many segments do you want to have lit up. And I'm decrementing this once. And then there's basically an if statement that says once this is below 0, basically switch off the serial thing, make it go low. So we begin shifting in zeros instead of ones. And what this is doing then is just pulsing the clock on and off. And there's actually a little delay in there that I put in there just to visualize it nicely. But if I'm actually using it, I'm going to leave out the delay, because else you can see the data shifting in, which you don't want. And that's basically how this works. It's a little sketchy, but it seems to work just about right. And this is what that bit of code does. I currently have it set to 5, and you can actually see there's 5 LEDs lighting up. What you can't see on camera is that this LED is flashing every once in a while. You can actually just barely make it out. Certainly not in a way that's actually any annoying or any visible if you don't concentrate on it, but it is definitely pulsing. That's because it's shifting the bits in like this from down here. And I'll just set it to some other value and re-upload the code. I actually see, bang, I set it to 2 now, and 2 LEDs are lighting up. So what I'll do next is I'll put a little delay on the clock so I can actually see how it is shifting it in. So that's it, with just a little bit of delay on it. So I slowed it down a little more, and I can actually properly see 1 lights up, 2 light up, and then it just gets shifted to the end here. And since this is not all the bits in the shift register, there's actually a bit at front missing here that you can't see, but that's alright. We're going to have less than no, we're actually going to have exactly 6 segments on this, because we're shorting the last 2, or the last 2 on this side. So yeah, I'll call this a success. Works just about fine. So for the actual audio and Bluetooth part, I'm just going to be a bit lazy, and I'm going to use those pre-built modules. These pre-built modules. This is a Class D amplifier, 20 watts, I think 10 and 10. It's based on a YL 2020, so it's probably 20 and 20 watts, but we're not going to drive anything up to 20 watts. That would be ridiculous. This is just a little Bluetooth module. You can get those very cheap off of eBay, and I think this is type XY BT Mini, and these especially are fairly useful because routing your own Bluetooth antenna on a board and doing all those things, even if you found a nice chip that you could design this into, there's actually not that many passives on there, about 10. And there's almost nothing on the back layer, but there's a lot of VS stitching around the antenna here. So I reckon this is probably hard to do, and you'd probably have to do some math to actually get the antenna right, or just copy it off the datasheet if they provide you with that. But then again, this is a Chinese chip, I think, and there's probably a Chinese datasheet for it, which, it's not that hard to read, but you don't necessarily want to do that either. So, pre-built Bluetooth module and pre-built Class D amplifier. What you could also do, if you just want to go the extra mile and make something that's a little more fitting, you could use something like this PAM 8040 something. PAM 8403. They don't sound that great, but they're very easy to do even on a single layer board. Yeah, you could build yourself, I think, 5 and 5 watt Class D amplifier. Or if you would want to do something even better, there's a nice chip by Yamaha that I tried to design into a previous project, but I didn't. I'll have to do that someday. And the part number is JDA 138. They're a little bit bigger, and you have to provide a thermal pad, but those sound fantastic. Also compared to this it sounds alright, but it's not brilliant. The nice thing about these boards is you can actually, they're designed so you can have them in there with a little with a header as a little daughter board. So yeah, these are incredibly convenient. They don't sound too bad. So I think we have almost all of the stuff figured out. Well, except for maybe driving the VFD display. No, VF display or VFD. But yeah. So let's just look at the schematic here real quick. We've got the charge circuitry with the LM317 here, then the balancing circuit that we also talked about here, simple on off switch here. This just goes to the 12 volt power rail where all the things, I mean the 12 volt output and also the actual Class D amplifier module attached. We've got a step-down converter here. I still have the current limiting resistor in here. I'm not sure if I'm going to need that yet, but it's designed and I'll just bridge it if I happen to not need that. Then we've got a step-down converter circuitry here. I'm going down to the 5 volts, powering the microcontroller, shift register, Bluetooth receiver module. Also put 2 pots in here, so I can basically factory trim the voltage down, the volume down. You're going to do the actual everyday volume adjustment, obviously over the Bluetooth thing, but since I have a fairly powerful amplifier here, maybe I need a sort of a divider to match the power output of the amplifier module to what the Bluetooth module is sending and what the speaker can actually tolerate, because I'm going to have 2 5-watt speaker, I think 5-watt maximum power speakers in here, and this can actually deliver up to, I think, 15 watts. So some care is needed to avoid overloading speakers. Then I have the supply for the VFD up here with the filament supply and the resistor network that just brings down the 12 volt power to these pins, and then the ULN 2003 that just shunts the biasing voltage that you get from the resistor network down to ground, and that is in turn activated by the shift register, which is activated by the microcontroller, and the microcontroller also has a voltage divider to sense the ADC voltage, sends the battery voltage over its ADC to decide on what to display. And that's just about it. So assembly and case design and board layout will be in the next video, because I'm still waiting on some SMD versions of parts, especially the shift register. I don't have this in SMD, and I want to do most of this in SMD because it just eases up on assembly. So I'll get back to you once I have all of that done and all the parts have arrived. But since it's Chinese New Year, that will probably take some time.